Good morning, everybody. I want to kind of do a supplement here for hypothesis testing since there seems to be some struggles with it. And it is kind of a tough concept to wrap your head around. In hypothesis testing, what we're going off of is something called the law of unlikely events. And when we're talking about unlikely events, what we're doing is we're making the assumption that something is true. So generally it's something that's been established, the current standard, or maybe somebody else has made this statement, so we just assume it's true. Then we gather data. We select a sample and gather data. And here's where it really kicks in. If those results, by the results I mean this data I gathered here, are extremely unlikely, given this, and by this I mean this top assumption, then the assumption must be incorrect. So what that means, let's say we assume that for a student, that we assume that their average GPA is 3.9. Okay, then we randomly sample their classes. Take a random sample of their classes. And let's say that sample gives a GPA of 3.71. And the standard deviation of all students GPAs is 0.09. And actually, let's do this. Let's make this a little bit more realistic. Let's say 0.6. We'll say the sample included 18 classes. So we took a random sample of 18 classes. So that's saying it's n equals 18 here. This, since all students, a GPA of the standard deviation was 0.06. So that is the population standard deviation, that's sigma. This here is x bar, that's my sample mean. That's going to be mu. So what we would set up here, we're assuming that this statement is true. So that's our null hypothesis, is that statement is true. The mean GPA, or their GPA, is 3.9. The alternative well, if it's, we said at least 3.9, so our alternative would be less than 3.9. So again, this is what we are assuming to be true. That's our assumption. Then we gathered this data here from this sample. Now the standard deviation here of the population had to be given. So that means since we're given that standard deviation of the population, that means we are doing a z-test. Or we are using a normal distribution. So let's say we want to test, and this part you must be given as well, test at, I can draw it alpha, I'm not typing here, test at alpha equals 0.05. So this is your level of significance. Or your significance level. And that is used to find your critical value. There's two things that are used to find your critical value. The alternative hypothesis and alpha. And of course the fact that this is a z-test. But here's our curve. This is saying less than. The alternative hypothesis is saying less than, which is telling us we're going to reject on the left tail of this. And the area in that left tail is given by our level of significance, 0.05. So that's telling us is we need to find the critical value is the z-score here that corresponds to that value of 0.05. Now we could find it on the calculator. We've done that. Second distributions, inverse normal is 3. Just type in 0.05 and it spits out a z-score of negative 1.6445. Or we can do it in Excel. You have to do equals norms inverse. You have to have the S in there, N-O-R-M-S-I-N-V. Otherwise, you have to include a mean and standard deviation. Of course, now being a standard normal curve, the mean would be 0 and the standard deviation would be 1. But I'd rather not enter them. And here we get the same thing, negative 1.64485. So that is a negative value, negative 1.64485. So what that's telling us is our rejection rule. The book doesn't necessarily use that term rejection rule, but it's what it tells us to reject is we will reject the null hypothesis, H0, if the test statistic, Z, is less than negative 1.645. We're going to round it to. So what that's saying is, based on this assumption, based on H0, our null hypothesis, it would be extremely unlikely to get a test statistic less than negative 1.64485 or negative 1.645. So if we do actually get a test statistic that's below negative 1.645, then we must assume that initial, or we must conclude, I should say, that initial assumption was not correct. And if that initial assumption is not correct, the only alternative is the alternative hypothesis. So let's check out this data here. Let's find our test statistic. So we found the critical value. That's one of the first things we have to do once we've set up the hypotheses. So number one step is to set up those hypotheses. Number two step, we have to be given alpha, that level of significance. So we use that level of significance and the alternative hypothesis to find the critical value. Step 3 is going to be to find the test statistic. So the test statistic here is going to be found off of the hypothesized value minus, the sample value, I should say, minus the hypothesized value over that standard error. That standard error is the population standard deviation divided by the square root of n. Of course, that is Z, our test statistics. This is the Z test. So we're given the sample gave us 3.71. We're subtract for that 3.90. We had a standard deviation of 0.6, and that'll be divided by the square root of, what was it, 18 is our sample size? 18 is our sample size. Now we should note, by the way, that since that sample size is smaller than 30, we have to know that the population is normally distributed. And I'm just going to tell you that yes, the student GPAs are normally distributed, so we can go ahead and do this test. If that sample size is not greater than 30, we have to make sure that. If the sample size were bigger than 30, it doesn't matter whether those scores are normally distributed or not. So 3.71 minus 3.90 is a negative 0.19. In fact, I'm just going to show you how to enter this all into any calculator. It doesn't have to be a graphing calculator. You just do parentheses 3.71 minus 3.9, close parentheses, divided by, then open parentheses again, 0.6 divided by square root of 18. Now, some of your calculators you have to do a close parentheses to end the square root. Some of them you have to do what I just did, do an arrow to get out of the square root. You have to do close parentheses again. Get a negative 1.344. So that is your test statistic. Now going back up here, we have to compare that to this test statistic, or our critical value of negative 1.645. So since the test statistic of negative 1.344 is not less than the critical value of negative 1.645, we fail to reject HO. So in other words, there is not enough evidence based on this sample. There's not enough evidence to conclude that the student's GPA is less than 3.9. Or in other words, there's not enough evidence to refute the claim that the student's GPA is 3.9. So that was a one-tailed, left-tailed test. And you can see here, all we really needed Excel for was to find the critical value. Now we could do a p-value on this. If you want to do a p-value test, well then the rejection rule, you don't need to find a critical value for doing the p-value. Your rejection rule is you'll reject HO if the p-value is less than alpha. So in this case, alpha is 0.05. So we'd reject HO if the p-value is less than 0.05. Now, for a p-value test, it's always this way. You always reject if the p-value is less than alpha. That's always your rejection rule. For the critical value, like we did up here, your rejection rule depends on the alternative hypothesis. This was less than here because the alternative hypothesis was less than. So anyway, how do we find the p-value? Find the p-value of our test statistic. Of negative 1.344. So once again, we look at that alternative hypothesis. The alternative hypothesis was less than, which is telling us we are concerned with this tail of the distribution. So we're going to plot that negative 1.344 there. And since we're concerned with this tail, we're looking for this area to the left of negative 1.344. So in Excel, we're going to equals norms dist. Again, we use the NORMS is saying that this is just standard normal. And we get, so then all we have to do is put in that test statistic if we use the norms dist. So rather than using norm dist, we use norms dist. So we don't have to put in the mean and the standard deviation and then true or false. So we get 0.0895. So that's saying is this probability here is 0.0895. So the p-value is 0.0895. So since the p-value of 0.0895 is not less than alpha of 0.05, we fail to reject that null hypothesis again. In other words, there's still not enough evidence to claim that their claim of a 3.9 GPA is incorrect. You'll notice we got the same result from the p-value we failed to reject as we did from the critical value. We failed to reject there as well. That should always be true. There should never be a case where one of them rejects and the other one fails to reject. It is the same test. It's just kind of different versions of the same test. You're using different details of the same test to decide what your conclusion is. The process is pretty much the same. You have to still do the test statistic and everything for the p-value test. So let's look at some different tests. Let's say that we claim semester cost is at most $4,500. So what that means is we are going to set up a null hypothesis. The mean cost is $4,500. The alternative, H1, I don't have to leave those up anymore. I can put in subscript. H0 and H1. The alternative, this is saying is at most 4,500. So the alternative would be it's more than 4,500. We always put equals in the null hypothesis, but remember, once we see that this is greater than, we know that really is talking about it's less than or equal to 4,500. But it's just kind of the grammar of the test. So we need to know some things. First of all, we want to test at, I can draw out alpha. I'm so used to typing this in, at alpha equals 0.10. So we're changing our level of significance again. And that's it. So let's say a sample of 40 students gives a mean of $4,610 and standard deviation of $180. First thing you'll notice here is I did not tell you the population standard deviation. This standard deviation here is from the sample. That means this is going to be a t-test. The previous example we were given the population standard deviation, so we could use a z-test. We would be using the normal distribution. We're using a t-test, that means we have to use that t-distribution. So now we need to find our critical value. For our critical value, remember, we once again need the alternative hypothesis is saying greater than. So that is telling us we're looking at it. The t-distribution is still a bell-shaped curve. Greater than means we're looking at the upper tail, somewhere up in here. Then we also need the significance level, alpha. which is 0.10. So we know that probability in that tail is 0.10. What that means is the probability on this side has to be 0.90. 1 minus the 0.10. Because remember, the whole area under that curve is 1. So what we're looking for is the z-score, or actually in this case the t-score, that corresponds to that 0.9 probability to the left of that mark. So on the calculator, it would be inverse, or second distribution, inverse t, which is option 4. 0.9, and we have to put in our degrees of freedom. There's 40 in the survey, so degrees of freedom are 39. It's giving us a 1.304. Notice that one's positive because we're on the right side now. In Excel, we do the same thing. It's T inverse, 0.9, and 39 degrees of freedom. Oops. What did I do wrong there? Oops, this one do 0.1, sorry. So in Excel, the T inverse function always assumes it's two-tailed. So this is where it gets a little confusing using Excel. A single tail here contains 0.10. Well, Excel won't let us do a single tail. So what we have to do is we have to be using this curve here, where we've got 0.10 here and 0.10 there. We just assume the other tail is symmetrical. Adding that together would be 0.20 total. So in Excel, what we are entering here is equals T inverse 0.20 and 39 degrees of freedom. Gives us that same 1.304. So you cannot enter a one-tailed probability in Excel. At least I don't believe you can. I don't see anything. I'll play around with these a second. Okay, I take that back. In Excel, there is a new function now in the newest version of Excel that actually allows you to use the T inverse exactly like the normal inverse. So we're going to do it's T dot inverse, INV. And we're going to put in that 0.09, or 0.9, I should say, is that probability to the left, and 39 degrees of freedom, just like we did with the normal. So you just did with the normal distribution up here. You did norms inverse 0.05. We would have had to have done 0.95 if it was on the right tail. So same here. The left tail probability is 0.90. And there's 39 degrees of freedom. So that does give us the 1.304. So they do have an advanced function that does one-tailed inverses in Excel now. So remember, that is T dot inverse. You have to have the period in there or it won't work. So that means 1.304 is our critical value. So we will reject HO if our test statistic now, which is going to be T, is greater than 1.304. Why did we use greater than this time? Well, because the alternative hypothesis this time was greater than. That always helps us with our rejection rule as well. So let's calculate our test statistic. We have our test statistic here. T is going to be our sample value of 4610 minus our hypothesized value of 4500 over, then we got to do our standard error. It'll be the standard deviation of 180 divided by the square root of sample size, which is 40. So again, I'm just going to do this in the calculator. Parentheses, 4610. Oops, don't need to close the parentheses yet. Minus 4500. Now I'll close the parentheses. Divided by, open parentheses, 180 divided by the square root of 40. Again, you either have to close the parentheses on the square root and then close the parentheses again, or you have to arrow out of the square root and close the parentheses like I did. We get 3.865. That's our test statistic. So since the test statistic of 3.865 is greater than the critical value of 1.304, we will reject H0. So what that is saying is we will reject H0, and there is sufficient evidence to conclude that the price is higher than $4,500. So we're saying that it is not true that it's $4,500 or less. What if we had to do a p-value here? Well, again, since that alternative hypothesis is greater than, we are interested in this upper tail of the curve, the greater than tail, if you will. We got a test statistic of 3.865. We know the probability of being greater than that. So on our calculator, we would go with second distribution, T CDF. Remember, it's always cumulative distribution function. So it's option number 6. 3.865 to saying greater than 3.865 is saying from 3.865 to positive infinity. So it's going to be, I just use 6 nines for positive infinity. It's easier than doing the 1 in scientific notation, the second EE 99. And we do have to put in 39 degrees of freedom. This throws it back to us in scientific notation. 2.046 times 10 to the negative 4. Remember, this times 10 to the negative 4 just means that decimal point has to move 4 spots this way. So that's 0.0002046. 0.0002 is probably far enough. To do that in Excel, now since it's greater than, remember Excel always does less than, so we got to do 1 minus. It's T dot distribution, 3.865, 39 degrees of freedom, and we do have to put in true for cumulative. This is a cumulative function. And we get 0.0002, exactly what we had before. So that's our p-value, and since the p-value of 0.0002 is less than alpha of 0.10, we reject HO. So again, both tests rejected the null hypothesis, and we concluded that the mean cost per year is actually, or per semester is actually more than $4,500. That assumption of being at most $4,500 is not correct. Well, let's look at one that's two-tailed. Let's say that we assume the mean weight of students is 180 pounds. And we're given population standard deviation is 30 pounds. So since we have the population standard deviation here, that tells us this is going to be a z-test. Or in other words, we're back to using the normal distribution instead of having to use the t-distribution. Based on this, let's get our hypotheses. Now, it doesn't say at most 180 pounds or at least 180 pounds. It just says 180 pounds. So that's telling us that the mean is, we're assuming the mean is 180 pounds. So the alternative is that the mean is not equal to 180 pounds. By saying not equal to, we're saying we will reject if we get a value that is too large, or if we get a value that's too small. A value that's too far away from that hypothesized mean of 180 will reject it no matter which side it's on. So let's gather data. So let's say a random sample of 100 students gives a mean weight of 172 pounds. Still have to give you alpha. Test at a significance level of 0.01. So again, for our critical value, we use the alternative hypothesis, and as we stated, since that's not equal to, that's telling us we're going to reject on either tail here. Alpha of 0.01 means that probability is 0.01. That has to be split evenly to both tails. So 0.005 here, 0.005 here. This is a z-score, so we need to find the z-score that corresponds to either 0.005 or this would be 0.995 up here, 1 minus the 0.005. I can do either one. So on the calculator, it would be second distribution. Inverse normal, 0.005, is going to give us the negative one. Negative 2.576. I'll write it down here quick. This then, of course, would be positive 2.576. So those are our critical values. In Excel, it's just equals norms. Remember, I have to have the S in there. Inverse 0.005. There the negative 2.576 again. So what this is going to say, because we have an alternative hypothesis that's not equal to, we have to reject on both tails. So we will reject HO if the test statistic Z is less than negative 2.576, or if Z is greater than positive 2.576. So now we find our test statistic. It's going to be our sample of 172 minus the hypothesized value of 180 over, we have a standard deviation of 30 divided by the square root of 10, or 100 I should say. So again, let's just punch that in the calculator and see what we pop out. So parentheses, 172 minus 180, close parentheses, divided by parentheses, 30 divided by the square root of 100. Make sure we close off that second set of parentheses. A negative 2.666. 2.667. That is slightly less than that critical value on the left side of a negative 2.576. So here we reject on this part of the rejection rule. So since our test statistic Z is of negative 2.667 is less than a critical value of negative 2.576, we reject HO. And we conclude the mean weight of our students is not 180 pounds. What if we're looking at p-value? Well, for p-value, again, the alternative hypothesis tells us what tail we're interested in. Since it's not equal to, we're interested in both tails. So what we have to do is we have to use our test statistic, which is negative 2.667, and its mirror image, positive 2.667. We need to find the probability of being outside. Well, what we're going to do is we're just going to find this probability. The left side is always easier to find because that's what our Excel is aimed for, and the calculator can be used to find that as well. We want to find that probability, then we'll just double it because this will be the same. So we'll just take this one times 2 to get the total p-value. So that's going to be less than negative 2.766. So on the calculator, it'd be second distribution. Negative, make sure you use that for the negative and not the minus sign. Oops, I got to do the normal CDF, since this is a normal. So now it's negative 999999, comma, now my test statistic of negative 2.667. That gives me 0.0038. We multiply that times 2, we get 0.00765. Let's double check this in Excel. In Excel, we're looking at less than, so it's just going to equals norms dist. Remember, we have to have the S in there of negative 2.667. And there it is, 0.00383. We have to multiply that by 2 again, just like we had to do here. So equals that times 2. 0.00765, which is exactly what we have here. So since p-value of 0.00765 is less than alpha of 0.01, we reject HO. So that should be the nuts and bolts of hypothesis testing with using either the calculator or Excel. So basically all Excel does for us here is help us find the probabilities and the critical values. The rest of it has to be done on its own. Now the previous video I have posted shows how you can use the calculator to do the complete test. So I'm not going to repeat that process here, but you can go back and look at the other video if you would like to see how the calculator, if you have the calculator, will do that complete test for you.